Um, okay, so let's switch gears a little bit and talk about dummy variables. And I have this slide called Dummy Variables Are Smart. So they're not dummies at all. So one thing that you can do with multivariable regression or linear regression, but this is interesting in the context of multivariable regression, is to fit factor models that include like a mean for group 1 and a mean for group 2 and test the difference in the means. That doesn't inherently seem like a regression problem, but in fact it is. So imagine if our variable x is, instead of the only two values it takes, is 1 if it's in a group and 0 if otherwise. So treated versus not in a clinical trial is a great example. Okay, well then for the people in the group, right, the linear model predicts this: expected value of y is beta naught plus beta 1. And for the people not in the group, then xi would in that case xi would be 1. And then for people not in the group, xi would be 0, and then this term would drop out, and then the model would predict that. So this is basically saying there's a mean for people in group 1 and there's a mean for people in group 2. And we can actually interpret what beta 1 means in this case, the coefficient in front of x1. Let me get rid of some of those marker drawings so I can draw some more. So notice what beta 1 is if we subtract these two, it's the difference in the means between. So this was the group, the mean for all the observations in group 1, and this is the x equal 1 group, and this is the mean for all the observations in the x equals 0 groups. And so if we subtract those two, we get beta 1. So beta 1 now is interpreted as the increase or decrease in the mean, comparing those in the group to those not. Okay. In this case, right, if beta 1 is positive, then that is the increase for the group where x is labeled 1 relative to the group as x is labeled 0. If beta 1 is negative, then that is a decrease in the mean for the group where x is labeled 1 relative to the group where x is labeled 0. Note, by the way, again, just by the rule that we had on the previous slide, if you know someone is in group 1, let me say this. So if xi1 is our variable that's 1 for those in the group and minus 1, 0 for those not in the group, then including a variable that's 1 for those that are not in the group and 0 for those who are in the group, that variable just turns out to be 1 minus xi1. You can double check that, but it's pretty clear, right? When xi1 is 1, it's 0. When it's 0, it's 1. So it just reverses the 1s and 0s in this binary variable. So this is a linear, and our intercept is a regressor with just the 1. So this guy is exactly a linear combination of our existing variables, right? So it can't provide any new information, so it will give you an NA. Okay, just like on the previous page. So that's this point right here, which says including a binary variable that's 1 for those not in the group is redundant, just like we talked about in the previous page. And there's nothing specific about two groups, treated versus control. We could do factor variables with multiple groups. Let's say it's a 3-factor level. So imagine you wanted a predictor to be party affiliation: Republican, Democrat, Independent. Those are the most prevalent, the 3 most prevalent U.S. political affiliations. So imagine a model now where yi is beta naught plus 1. That's an indicator if you're a Republican, and 0 if you're not a Republican. So if you're a Democrat or an Independent, and we're assuming everyone in this data set falls under one of these 3 categories. xi2 is 1 for Democrats and 0 otherwise. Okay. Then let's look at what happens. Then the expected response for Republicans is beta naught plus beta 1, because beta naught is always there. xi1 is 1 when when the person is a Republican, so we get a beta 1. This guy's 0, okay, and this guy's expectation is 0. So we get that for Republicans. Similarly, we get that for Democrats. And then for independents, both this guy and that guy are 0, so we get beta naught. So how do we interpret these coefficients that come out of the linear regression model? Well, beta 1 is then, if we were to subtract these two, the beta naught would drop out and we would get beta 1. So it's clear that beta 1 compares Republicans to independents. Beta 2 compares Democrats to independents because it's just subtracting these two. So that, notice what that means is none of our coefficients compares Republicans to Democrats. What compares Republicans to Democrats is a function of our coefficients, beta 1 minus beta 2. And notice this is all predicated on which one we chose as our reference category, right? We elected in my previous slide to have xi equal 1, say, be treated in 0 equal control. And then we would get one interpretation if we did xi equals control and xi equal 1 as control and x equals 0 as treated, we would get the opposite interpretation. In this case, we have to choose. We included a binary variable for Republicans, a binary variable for Democrats, and omitted the binary variable for independents. If we had omitted the binary variable for Republicans and included the binary variable for independents, then in that specific case, the Republicans would be the reference category. They would be the ones with only the intercept. So choice of the reference category changes the interpretation. Then the beta 1 and beta 2 from the model would be corresponding to comparisons relative to the Republican reference category. Now, because we omitted the independent xi, then everything is interpreted relative to the independence reference category. Okay? Let's go through an example. Here's a nice categorical example where they sprayed a bunch of insects and they got the count of I think, can't remember if they're counting dead insects or live insects. Let's well, it depends on your opinion. If it's a nasty insect like fleas or cockroaches, let's assume they're counting dead insects. If it's a nice insect like ladybugs or butterflies, then let's say they're counting live insects. Okay, so let's assume that's the case, and then we want to let's just spray, of course. So they're of course counting probably they're probably kind of nasty insects, so cockroaches or fleas or something like that we don't like. Then they want to see which one of these insect sprays, if the mean count for each of the, I don't know why that's doing that, differs for each of the groups. Now there's clearly some problems here. These are counts, so we shouldn't be fitting them in a linear model, but we're going to do it anyway. And there's clearly a variance issue, right? These guys, first of all, there's an obvious effect. You don't really need a lot of statistics to see that C, D, and E seem to have a lower effect or have a different mean than A, B, E, and F. And you don't, you can see this variance problem, that the variance is not constant within groups. So the constant variance is clearly a problem. And then the fact that it counts, clearly that's a problem also. So all of those are issues. All those are issues in this data set, but we're just really trying to use it to illustrate group factors. So let's actually do it. And this will show you how the model can quantify the changes in those means. Again, pointing out all these caveats on why this isn't a terribly good analysis. So summary just gives the summary of the output. LM is our linear model function. Count is our outcome in this case. Number of insects we zapped with this particular spray. Here's the spray. Is the factor variable that has all the levels. Okay, so when you put a factor variable in, R automatically creates the dummy variables for you, and it uses the one that's the lowest order factor, and if it doesn't know, it uses the one that has the sort of alphanumeric lowest value. In this case, A has the lowest value, so it's the reference variable, but it picks that for you, and we'll show you in a slide how you can reorder it. So data equal inspect sprays tells you which data you're looking at, and then just coef from the summary function is just grabbing the table. I just wanted the table. I didn't want all the other output because then it gets too big on my slide. Okay, so what's important to note is that right here, right, it has every spray B, C, D, E, F except A, and that's because R has elected to choose A as the reference category. So this coefficient for spray B is the estimated expected increase in insect count comparing spray B to spray A. And it's B minus A, okay? And this is for expected count for spray C minus spray A, okay? And you can double check, right? Like, so spray A has a lower coefficient, spray A has a lower coefficient than spray B. Spray B has a higher coefficient. Spray C has a lower coefficient than spray A. Spray D has a lower coefficient than spray A. Spray E has a lower coefficient, and spray F has a higher coefficient. So let's double check, just make sure it makes those make sense. But C, D, and E have these really small p-values and gigantic t-statistics. So let's just double check and make sure that's what's going on. Yep, C, D, and E were all lower than spray A, and it's clearly that should be significant. So that's the table's kind of working out the way we'd hope, or the way it must. Okay, let me just show you that you get the same thing if you code it exactly yourself. So imagine this indicator is just, this double equal sign is just testing the Boolean value of whether this spray happens to take the value B, and then I multiply it by 1 because it changes it from Boolean to numeric. And then the I is just a function in R you have to do if you're doing some mathematical manipulations in a model statement, which is what follows a tilde sign. Okay, so I put, this variable here, which is included in the regression model, is 1 if spray is B and 0 otherwise. Okay, and so this just hard codes all the 0, 1 variables. You could actually just put them in the data frame, you could do them, but I'm doing them in the model statement here. And you can see you get the same numbers, right, as before, right? So 0.833, negative 12, negative 9, negative 11, there they are again. You can see they're the same. Okay. What happens if we include all 6? Okay, what does it do? Well, first, so I'm including an extra variable, and this one is clearly redundant because let's say, so I have x1, x2, x3 up to x6 that are all binary, right? And x6 is equal to 1 minus x1 minus x2 minus x3 and so on, minus x4 minus x5, right? So we have, by including the intercept, we have a 1 in the model, we have x1, x2, x3, x4, and x5 in the model. So if we know all those, then we know x6. And that's, of course, just saying that if we know you're not spray B, C, D, E, F, then you must be spray A. That's all it's saying. But it's also relative to our rules that's saying we know that the indicator of whether you're spray A happens to be a linear combination of the other sprays and variables that we've included in the model. So this variable must be redundant, so when R fits it, it's got to give it an A. Now R has to have a rule for picking which one of these guys is redundant, and it's doing the last one, and because it doesn't know anything about the letters in the way that I've formulated the model here, right? It just has a bunch of 0, 1 variables. But when you include spray as a factor variable, it does this for you, and it doesn't even put the NA in the output. So that's nice. So you never kind of do things this way. I was just showing you. Well, I sometimes do them this way. If you want to be 100% sure that you have your dummy variables set right, then you do them yourselves. Otherwise, you can just trust the factor, that treat a variable as a factor variable, and it'll usually do it correctly. Here's another interesting fact, right? So on the previous page we talked about how x6 is a function of the others if you include an intercept. You need that 1. If you don't include the intercept, it's not a function of the others, right? It's no longer redundant. And then what happens, right, is then here, if you omit the intercept, then it includes all 6 sprays. So that, that again makes sense, because now spray A isn't a linear combination of the other sprays. The spray A indicator is not a linear combination of the other sprays. But it's basically just saying, think about it this way. There's 6 means in this data set. And then the intercept gives you the mean for spray A in this case, and the intercept plus beta 1 gives you the intercept for spray B in the case where we include the intercept. So there's 6 means, so we can't kind of include a 7th, in there, and so there's 6 means. So there's really that's all we can fit. So it can only really fit 6 coefficients. So if we include the intercept and there's 5 sprays, it's got to get rid of 1 and have only 5 coefficients, because 1's going to the intercept. If we omit the intercept, then we have 6 means that we need to fit, and we have then 6 coefficients that we can fit. And it says, oh, okay, well, I'll do that. I'll include 1 for spray A. And what you'll notice then, in this case, now the model is yi equals, let's say, xa plus, I need an eraser. Is that y is equal, I'm just going to kind of do pseudo notation, is equal to beta A xa plus beta B xb plus beta C xc, and so on, right? And so the expected value of yi, if that happens to be in spray A, it turns out to be beta A. The expected value of y, if it happens to be for spray B, it turns out to be beta B, and so on. That's the model in this case that we fit. And so these should be these should be the means for each group. Okay, and so let's double check that. So spray A, it's saying the mean should be about 14, and for spray B the mean should be about 15. For spray C it should be about 2. Let's just go double check back here, and it makes sense, right? Spray A mean about 15, spray B, somewhere around 16, spray C somewhere around 2. Okay, that seems about right. These are the medians, but it's close enough that we know. And what I'll tell you, you can check this yourself, and it's maybe a little bit hard to see why it works out exactly this way, but these are exactly the mean. So if you just calculate the mean of the counts in group A, it'll be 14.5. If you calculate the empirical mean of the counts in spray B, it'll be 14.5. So if you do the outcome, you do your factor variable, and you omit the intercept, then it will fit a term for each one of those, and the interpretation of the terms will be the mean for that group. And if you want to compare A to B, then you have to subtract 14 and 15. Now you don't have the right standard error, so you don't have a p-value or a t-statistic, but that would give you the correct estimate. And what you'll notice is if I were to subtract 14 and 14.5 and 15.3, then I'd get exactly then I get exactly 0.833. I get this value right here. In other words, the models are perfectly consistent. If you're going to fit 6 means any way you do this, and the models will always be consistent. So if you parameterize the model so all the coefficients are interpreted as A as the reference categories and change from A, then they will be consistent with this model, where the coefficients are interpreted as the means for each group, and if you were to subtract any of the two groups, you will get, or if you were to subtract any of the groups from A, you will get the coefficients that you had from the model where A is the reference category. If you were to subtract the coefficients from B, you would get the coefficients from the model where B is the reference category. Oh, here I actually do, where I just take the average of the within each of the groups, and you can see it's 14, 15, 2, 4, 9, you know, that's exactly what we got right here. Okay, so at any rate, my points, let me see, my points. Okay, if we treat spray as a factor, R includes an intercept and omits the first level of the factor. And then all of the t-tests and all of the coefficients are interpreted except the intercept are comparisons of that spray versus spray A, and the intercept is interpreted as the mean for spray A. Okay, that's right there. And the other group means are the intercept plus their coefficient. Okay, if we omit an intercept, then it includes all terms for all levels of factors, and then the group means are the coefficients. And the t-tests are no longer for comparisons between the groups. They're tests for whether or not the groups are different from 0. And then if you want a comparison between, say, B and C or model C, what you could do is you could refit the model with C as the reference category or B as the reference category. Okay, that's the kind of lazy way to do it. I'll show you well, I don't know. That's the intellectually lazy way to do it. The lazy but knowing how to do it way to do it is to simply use the relevel function. This is just basically saying I want C to be my reference category, and then I just fit my ordinary thing, and then now spray C is my reference category. Notice there's an effect for A, B, D, E, and F, and an intercept, and C is the one that's omitted. Now this 12 is the subtraction between spray A and spray C. Okay? And so your p-value is interpreted as a comparison relative to spray C. And then just because I'm this kind of person and I like to futz around with things at this level, you could actually figure out how to do it manually. So if you were to, for example, fit the model where A is the reference, what you could do is you want to subtract the B and C coefficients and get the comparison between B and C. Well, the variance of that is the variance for the B hat for spray B plus the variance of the B hat for spray C plus minus twice the covariance. Okay, so here we've fit the linear model where A is the reference category, and then here is just subtracting the B and C coefficients, which will correctly give you the thing as if you would fit C as the reference category, but it doesn't give you the standard error. Okay? And then let me just take the summary of that fitted model and just assign it to a variable. And then what I want to get is the standard error of that comparison, and that's the let's see, so that is the this guy here, right? That's this term. This is this term, and then minus twice the covariance is that term. Okay? And there's our t-statistic being the sum, the effect divided by the standard error, and the p being the absolute value of the t-statistic, the p-value being I always take the net. So right here's our t-statistic. We want the probability, if it's positive, of being above it. If it's negative, we want the probability of being below it. And so I always just take the absolute value, get rid of the sign, and take the negative one, and take the probability of being below, because that forces it to be below 0. I should have put, let's see, I should have put a 2 there, twice that, if you want the two-sided p-value. The other thing I would say is, by the way, this covariance unscaled gives you the covariance not scaled, and so you have to multiply it by the residual standard deviation. Okay, and my out is, I'm defining just the set of things that I want to output, call it that, I'm giving it a bunch of names, and there you go. Round out 3 just means print it to 3 digits. So there's my estimate, there's its standard error, and there's its t-statistic. And so let's compare that in the previous page to the one where C is the reference level. So B minus C here is 13.25, and here it is, spray B minus spray C when C is the reference category is 13.25. The standard error is 1.61, 8.25, and then 8. You can see they're the same. So that's how you can do it without from the model that you actually fit, right? So you know what parameters you want, and you can calculate the variance, and you can just do it. Of course, that's not how you want to do it, right? You just want to re-level it so that C is your reference level. It's so much faster. But anyway, I don't know. This trick comes in handy for me sometimes. Okay, so some other thoughts on this data. Just I want to indemnify myself from this kind of sloppy analysis. The counts are bounded from below by 0, which violates the assumption of normality of the errors. There's counts near 0, so that both the actual assumption. If you have a bunch of counts and they're nowhere near 0 and they're nice and normally distributed, then even though they're counts, it doesn't matter. You can still use a Gaussian distribution for the residual. But these have counts near 0, so the actual assumption and the kind of intent of the assumption are violated. The variance doesn't appear to be constant. Maybe you could take logs. There are some 0 counts, so you can't take logs. So you can maybe do log count plus 1. But my favorite way to do this would be to do something like a Poisson GLM or a quasi-Poisson GLM or something like that. Then you don't have to worry about any of these issues.